All right, everybody, thank you very much for coming out to our talk tonight. We're really excited to have you here. The first talk of the year is always a fantastic talk, and tonight it's no exception. Anytime that we have someone talking about spy satellites, it brings out a great crowd, and I love this stuff. This is the coolest stuff. So I'm really happy that we're able to be here. A huge thanks to HBSR for hosting us tonight. We couldn't do it without them. They're phenomenal. So big round of applause. If you have any IP or patent attorney needs, go to them, please. They're wonderful. Three announcements, and then I'll get out of here and let our speaker do his thing. First up, this Sunday, September 21st, we have the Cambridge Science Festival. We are going to be hosting a table giving our usual demo of light across the rainbow. We have a thermal camera, we give out diffraction glasses, and we let kids play with fiber optics. And we have a really fun time showing children the nature of light. If you're interested in volunteering, I'm going to send out an email later this evening with logistical information to anyone who signed up. But you can go to our website, NES-Optica.org, sign up there to volunteer, and we'd love to have more help. It's always a great amount of fun. It's completely draining. Kids swarm you.
7 o'clock.
Fraction glasses. It's so much fun. So that's this Sunday, September 21st. October 8th, I believe everything's confirmed, right? Yeah, cool. We have another optics networking night. If you were there for the one in the spring, it's a great time. We go to a bar. We have a great tab open. You get to meet people from across the optics industry, socializing, making new connections, learning about your colleagues. No real speaker. The host this time is Axiom Optics, but it'll be at the Mighty Squirrel Bar in Fenway. So it's going to be sponsored by Axiom, but at Fenway's Mighty Squirrel. That's October 8th, 6 p.m. Again, NES-Optica.org. Sign up on our website. We'd love to see you there. No cost to attend that one. And then October 22nd will be our next talk. That one is going to be a really, really interesting one. That'll be a talk about orbital angular momentum entanglement in optical fibers. And that's going to be a PhD defense practice talk by aspiring a PhD student at BU, and that's going to be at a new venue. We're going to be hosting that at the BU Photonics Center, I believe. So that's going to be a really interesting talk. And if you've never seen the BU Photonics Center, it's beautiful, lots of really cool stuff there, and going to be a really interesting, sort of a more academic quantity talk. But without further ado, I think that's everything I have to say. So I'd like to hand it off to our host, our speaker tonight, Michael Clayton, to talk to us about early satellite reconnaissance. So big round of applause for Michael.
Okay, thank you very much. Can everyone hear me and see me and all that stuff?
All good.
Okay. What I want to talk about is sort of the story of how all of the imaging satellite stuff got started from a particular perspective. And so I'll cover all of the work that Kodak was involved in, which was quite substantial, and give you a flavor for what it was like then. And I'm going to start with a little bit of background as far as the kind of the environment that we found ourselves in. And so if you look at hang on a second here. Here we go. Okay. Okay. So if you look at the next thing, essentially, there were two key global factors that drove the establishment of a national reconnaissance program. During the Second World War, reconnaissance, aerial reconnaissance, proved to be critical, absolutely critical. And there was the amount of photography, aerial photography that was done was just mind-blowing. I had a good friend for a while who since passed away, who was a pilot of a reconnaissance aircraft flying a P-47 modified for reconnaissance over the enemy lines, behind enemy lines, and so on. And he says, you know, he was just consumed by that mission, and he wasn't the only one, obviously. So that kind of sets the stage for how important aerial reconnaissance is. And we go into the Cold War, and right after the war ended and all the agreements were in place, the Soviet Union threw up what was termed by Churchill as the Iron Curtain. And what that really meant was that there was no aerial reconnaissance over the Soviet Union. That was closed. And therefore, no one really knew in any detail at all what was going on in the Soviet Union at that point in time. And as things progressed, obviously there was an arms race. The Soviet Union began development of its own nuclear weapons program, um, and so on. So that kind of sets the stage. And then here's some of the key events leading up to satellite reconnaissance. And the real trigger for this was that in October well, actually a bit earlier in 1960, on May the 1st, Gary Powers flying the U-2 over the Soviet Union, which was a process that had been going on for not a long time, and was the first chance for the Western allies and the United States in particular to be able to get any reconnaissance data over the Soviet Union. And they shot it down, and it created a big crisis, and President Eisenhower shut down the U-2 aerial reconnaissance program. But in the background, starting let's say starting in about 1960 or thereabouts, a little bit before, in the 50s actually, the Air Force had started the program WS-117L. Some of you may be familiar with all this, and I apologize. I ask you just to bear with me. I'm not going to spend a lot of time on this. But what was known as the Discoverer program was the public thing, white name, so to speak, unclassified name, that people became familiar with it. I remember it much as a young man when I was still in high school, about the Discoverer program, and would make a big deal of shoot monkeys into orbit and recover them and all that sort of stuff. But there was much more to the program than Discoverer. Discoverer was the unclassified name for the part of the program that developed what are called recovery vehicles. And the intention there was to be able to return photographic film from orbit. And so that was ongoing. At the same time, the program looked at ways to get imagery directly from orbit. And Kodak was involved in that. And what we were involved in was using a film camera, which was the only way to take pictures at the time, with onboard processing, readout, and transmission of the imagery to Earth. And we had two basic payloads called E1 and E2. And we did, in 1961, we had one successful launch. Typically, well, this was all located on or launched on the Atlas. And the booster vehicle had a lot of problems. It seems like every single launch there was a problem with either the booster itself or with the attitude control system or something else. We finally got a payload to orbit in 1961. It successfully transmitted imagery back to Earth, and it met all the specs that had been set for it. But however, it turned out that the bandwidth available to transmit data at that time. It was an analog system, and we're basically transmitting a video signal from the satellite to Earth. And the only place that we were allowed to send information downlink was over the continental United States. So that limited the amount of time available and the ability to transmit lots of image data to the ground. And so the decision was made at that point that they were going to go with film recovery from orbit. And the first program to come out of this particular project was the Corona project, which you may be familiar with. And that was a wide area survey system. It was not a very high resolution, but it was able to cover lots of territory and provided some information on what was going on over the Soviet Union. So that was the very beginning that kicked off. A few years later, in around 1960 or thereabouts, when we started the Apollo program, NASA was interested in and had the need to map the lunar surface to help select safe landing sites for Apollo. And so what we did in conjunction with Boeing is we submitted a proposal to use the SAMOS technology and fly a SAMOS type system to the moon and transmit the data back from the moon to the Earth. And because of all the work and risk reduction that had been done on the earlier classified program, the proposal was the one selected to develop. And here's a kind of a block diagram of what that involved. And this was basically the same way that the SAMOS system worked. If you look at the top there, you'll notice that you have film coming off a supply reel, and then it goes to a camera, and it has edge data recorded on it. It's the image is exposed in the camera, and then it goes to a scanning system, which then was called a line scan tube, and it was a vacuum tube that had a rotating drum in it that had phosphor on it, and an electron beam would scan across the rotating phosphor dome, and it would give you a flying spot, which then was imaged through the film to a photomultiplier tube, generated the electronic signal, and that was converted directly to a video signal, and combined with some other telemetry from the satellite, and then transmitted through the deep space network to ground. The signal, when it came to the ground station, was recorded on magnetic tape, and then we took that and used what's called a kinescope, which is a way at the time that was used to record video signals on film. And then the data that came back consisted of a number of strips of imagery over a given area, and those were recorded on 35 millimeter film, and then it was reassembled manually and imaged onto 12-inch film, which was then used to generate the images of the moon. It's kind of a mind-blowing, complicated process, but the technology didn't support anything else at the time. So that's basically how the system worked. This is a picture of the satellite payload that we built that went to the moon. You'll notice at the top there, you see a thing there. That is actually the lens. That it was a 24-inch focal length lens, and then there was a much shorter focal length wide angle lens. There were two lenses that were used, and it was selectable. And that was how we imaged the lunar surface onto the film. The film that we used then was 70 millimeter film. And here's a picture this is in 1965 roughly, This was towards the end of the Lunar Orbiter program. This was the clean room we had, and there is a picture of the payload and being worked on. There is what we call the pig, which was what the payload that went into the spacecraft that Boeing provided, what it looked like. And there's another picture of the payload. And here's one of the first images that came out of there was a close-up view of the lunar surface. And you have to remember at this time, the only images of the moon that had any chance of showing much detail were taken with a 200-inch Palomar telescope from the ground. And they were not very good images. This kind of detail was just not available. Here's another shot of the Copernicus crater. And that shows, again, the kind of detail that we could capture with that system. The probably the most famous picture, which I didn't put in here since it's been widely shown, was a picture of the Earth taken from the moon. And that was the first image, one of the first images that was transmitted back, and it really kind of set the stage. Well, we went from Lunar Orbiter and CMOS technology to imaging the Earth in high resolution. Corona was starting to operate at this time. It was a large area survey system. It did not provide high resolution imagery. It just provided enough imagery to make you want something that you could use to see what was going on. And so that was the motivation for doing this. And when this all started, the decisions were made that set kind of the basic ground rules. And one of the key things is that all the systems operated in a sun-synchronous polar orbit. It has some real advantages. You can cover the complete Earth very easily, but at any given time of day, you will be over the same spot on the Earth. So, for example, if you wanted to take pictures of Moscow at 11 a.m. local time, you could adjust your orbital parameters and your launch times and all that so that you would always be over Moscow at 11 a.m. And the desirability of that is that for critical targets, you can adjust all your parameters so that the sun angle and the lighting conditions and everything else are optimized for maximal information collection. You can also adjust the orbit on the satellite, the apogee and the perigee, so that generally these were elliptical orbits, so that the lower altitude would occur over really critical targets. So if you knew that you were going to be over the Soviet Union, you would adjust it so that the apogee would be over the Soviet Union, and maybe the lowest point the perigee, and maybe the perigee itself might be over a particularly critical target area. And so it was quite really a nice way to do it. So, but there were two ways to get imagery back from orbit. We talked about the two that were examined in the early Air Force program, and we talked about why electronically transmitting imagery from photographic film was just not practical. And so the Corona used film return, which was the result of having the capsules developed on the Discoverer program to do that. And Gambit ended up using that. And Gambit was the first high resolution satellite reconnaissance system. So, you know, the Gambit got started in kind of an interesting way. As a result of the Air Force program, Kodak was also involved at this time in developing another system was called Blanket. And what it was a stereo system that used 36-inch focal length lenses. And the idea was to get stereo imagery over the Soviet Union or wherever we're interested, and get stereo imagery. Now, stereo imagery is nice because it gives you really a view of the, I'll call it the sides of the structure if there is such, and but it also gives you a lot of other information, including the height and so on of what you're looking at. And stereo imagery, if you've seen it or used it, you know it is really, you get a lot of really good information about it. Well, Kodak had its own internally funded studies going on and came up with using a 77-inch focal length camera to provide very high resolution imagery at that time. And also it would provide stereo capability. So it would replace blanket and it would provide better quality imagery. So that was, the Air Force then decided to accept that program, and they named the program Gambit. And then the question of security came at this point. The Air Force program had no special security arrangements. It was just what we would call normal security, which was not very secure in the sense that was judged critical that the Soviet Union not understand that we had any capability in this area and what its capability was. So initially the program was started as part of Blanket, which was a standard Air Force project, classified, I'm not sure at what level, probably secret or top secret. But then, and that was also being worked on by Kodaks, but that was common knowledge that Kodak was working on that program. So it was thought we could just sort of hide behind that and be doing this and no one would know what was going on. But it became increasingly difficult to hide it because the configuration of Gambit was so different than the blanket program that anybody that wanted to find out what was going on would be able to do so. So blanket was canceled publicly, so to speak, and Gambit was set up as a black program. Its existence and its identity were not acknowledged, period. And that was the security system that we worked under forever, basically. So the Gambit program went on from around 1961, and the last gasp of the program was in 1985, so quite a few years. Provided high-resolution photography. It was used for what was called technical intelligence, and it complemented the photography from Corona because Corona would provide the first look, identify potential targets that then Gambit could go and look at. The difference in the two fundamentally was the wide area coverage of Corona and the relatively small area coverage of Gambit because of its high resolution. And that was what continued for many years. So as we get into Gambit, there were a number of things that at Kodak we had to really pin down. First of all, what is the most critical customer requirement? And then how do you relate this to the design concepts that you have? How does the operating environment affect the system's ability to deliver that requirement? How can you predict the performance of the system? What are the test requirements that you need to have to verify the performance? And how do you set the specifications? And that leads to a key called systems engineering. And these are the kind of four key things that we started to use in a formal way. The highest utility characteristic that we developed was the ability to trace ground resolution throughout the system design. And so at each step, we would develop hardware and software specifications showing how they were traceable to the ground resolution, which turned out to be the critical customer requirement. So if you come up with a design for a piece of hardware, we had to develop the ability to link that design and its characteristics back to the customer's requirement. And over time, he developed an end-to-end model of the system design, which allowed pretty high confidence in the predicted performance. And we verified the model over time with actual data from testing and with actual experiments done on flights, as well as engineering knowledge that we had. During the project, the system engineers communicated and worked with the design teams very closely. And the idea was to assure that we had realistic specifications, meaning that they were achievable, but at the same time, we had to assure that critical requirements were met. And so we got into trade-offs between different system elements. So for example, you might trade off a smear requirement, an image smear requirement, which as we get into the system design, you'll see why that's important, against defocus or something like that. You try to bounce those back and forth, always looking at the performance of the system from the customer's perspective. And so that process continued throughout the project. So here was the basic tool that we used to drive this whole process. If you look at the modulation transfer function, and then the threshold modulation curve for the film, the intersection point is the predicted performance of the system. And whether it's imagery on the film or imagery on the ground, it's a scale factor issue. And so that was it. But the trick is to understand how these two key characteristics of the system were affected by the design of the camera system and by the environment and so on. And so that was what we really set about doing. So for example, the modulation transfer function was affected by lens aberrations, such as manufacturing quality, flaws in the design, damage or changes induced during the launch process, defocus, thermal effects while the system is operating on orbit, and the impact of the launch. Smears, basically the mismatch in film velocity to image velocity, and that can be induced by a variety of things, including just errors due to, let's say, failure on the part of the camera system in some way, the fact that you have discrete steps in film velocity, and so do you have enough of those, and are they accurately set so that they are what you think they're going to be? You have random smear with vibration, and then the vibration has other impacts on the hardware that may cause them to go out of spec. So all these factors affect MTF. And so the real trick here is to develop all the tools, analytical tools, test tools, and so on that you need in order to trace all these particular kinds of factors that affect the modulation transfer function of the system to, as you go through the design process. The threshold modulation curve for the films are affected by the granularity of the film, that is, the size of the film grains in the developed film, the sensitometric characteristics, that is, how does the film respond to range of illumination over the scene, what kind of processing you're using for the film, and the exposure that you set for the film, the exposure points against the scene characteristics, fogging or background radiation, stray light, of course, of all kinds in the optical system, the camera, and then radiation effects on the film, which increases the base fog level of the film. And you have to accommodate, you have to make sure you have set the right exposure time provided by the camera to agree with the needed exposure time given the scene characteristics. So there's a lot of things here that were unknown initially. And so for the first few missions, there was a lot of learning going on about how to set some of these parameters in the film, in the camera system. This is just the basic concept of Gambit throughout its life. You launch, you go into orbit, your orbital parameters are set based on the mission objectives. You collect imagery, you upload commands to the system, and receive telemetry back so you can gauge the health of the system and you can get the system to do what you need it to do. And then at the end of the mission, you eject your recovery vehicle with the exposed film, and it's actually dropped over the ocean. And we'd use an aircraft like a C-130. In the original program, Gambit 1, in the early days, there was no C-130. We used what's called a flying boxcar, C-119, to fly along, and would actually snag the parachute before the recovery vehicle hit the ocean, and you could reel it in, and then it would be taken off the aircraft and would be sent to Rochester, New York, and the film would be processed and so on right there. So that was the basic concept for the system. During operation, there were a number of modes that the Gambit system could come up with. The four key ones here called the lateral triplet, which is just a way to get, say you look at the ground track, which is the black line there, and you'll notice you might have a target where it was at an angle to the ground track you wanted to cover it. So that would require you to take successive frames and roll between the frames. The monoscopic strip, since this was a strip camera, which means the film ran continuously during exposure, and there was an open slit in front of the film where the image came. And so that was, as you flew over the surface of the earth, that image would move, and the film behind the slit would move at the same rate in the same direction if everything was working properly. So you could take a terribly long strip there. I'll talk a little bit more about how that worked inside the camera. And then your lateral pair is the same idea. It's as the lateral triplet, except this is just two successive frames. But the really interesting thing was we could take stereo photography. So quite a lot of it over, the ground track. It had to be taken from vertical, that is directly below the satellite. And the reason for that, we'll see in a minute. So here's a picture of the original Gambit 1 payload. And it'll start at the right-hand side. You'll see the primary mirror, and then you'll see what look like rods. Those are metering rods. And that goes up front to where there's another full aperture transparent glass collector or corrector. And the lens type was Maxitov, and it was developed by a Russian, believe it or not. And it was a fairly well-known design used for by astronomers and others. And so in front of the full aperture corrector, you can see there's something called a stereo mirror right here and a viewport. So the scene was looked at through the viewport over this mirror, folding mirror right in front of the telescope. And that mirror could move, rock back and forth so that you could look forward and aft a certain amount. And that's how you got your stereo. So you take a strip, part of your strip might be taken looking forward, and then the next section of the strip would be taken looking backwards. So where those two sets of images overlapped each other, you had stereo imagery. We could also rotate the mirror about the optical axis, and that also has to correct for misalignment of the satellite system with the actual motion of the Earth down below, and so it's called a crab correction. But right behind the full aperture corrector, there's a folding mirror that directs the imagery up to a camera, and that's where the strip camera was located. You'll notice the film loopers. The film loopers are really critical if you're not familiar with it. If you're going to take a picture of any length of time, you want to make sure that the film is passing behind the slit in the camera at an absolutely constant rate of speed as you need in order to reduce the mismatch between the film and image velocity. Well, you can't easily do that if you're pulling film off a very large roll of film. So what you do is you load the looper, it's like a buffer, and you store the film on the looper. It's very precise and it induces no vibration, or it's very smooth motion through the camera. And then you would have another looper on the output side that would collect the film as well, so that the passage of the film through the camera is extremely smooth and very well controlled and very precise. And then it would go from the output looper to the take-up reel, which is located in the recovery vehicle, which is at the left-hand side of the vehicle, through the film chute. And when you get to the end of the mission, there's a film cutter, and it's basically nothing more than a hot wire that chops the film off, and it's spooled into the recovery vehicle in its entirety. The RV is kicked out and it re-enters the atmosphere and is recovered. Now there are, in addition to just these basic things here, there's focus adjustment that's in there. And of course you need electronics to control the speed of the film as it moves through the camera, depending on what the image velocity is going to be. You have to maintain very strict temperature control inside, particularly in the optics, so that you don't induce any thermal distortions and degrade the performance of the optics. And there's a whole host of other things that housekeeping things that need to be taken care of. Now, this was the very first time that anybody had tried to build a satellite with this level of resolution at all, period. And so this was quite an exercise. Most of the stuff that we needed to learn when we started, we didn't know. There were some things that were known, obviously, but just many unknowns. We just didn't know how what the environment was really going to be like. We weren't sure what would happen and what the best way to have this precision instrument survive launch on the rocket system without being degraded. And as it turns out, there were just a whole host of things that went on. We ran into issues at the front end of the program because of this thing was operating in essentially a vacuum environment. Any moisture that was in the film itself would outgas, and then we would get into a situation with static electricity, and so then you'd get lightning bolts on the film, which is not a good thing. And so that was not an unknown problem totally, and we were able to figure that out. and provide conductive coatings that would help alleviate that issue. Radiation environment was not well known, and so we weren't sure what would happen. The starfish experiments where they conducted or fired off a nuclear weapon at high altitudes in orbit put a lot of charged particles into the Earth's magnetic field, and some of those were very energetic, and there was a lot of concern that we might fog the film and so on. And so we had to learn how to design so that we could survive that sort of an environment, and so on. So there were just some of the things that went on in the early days of the program. So in summary, for the Gambit 1, the first Gambit, the Maxitov lens, the aperture was 19.5 inches, 77-inch focal length. The stereo mirror I talked about was 33 inches in diameter. It was an f4 camera system, had a strip camera with commandable slit widths, film speeds, and also focus. We used type 3404 acetate-based aerial film, and the nominal operating altitudes were 65 to 90 miles. And better than 3-foot resolution is what the government was willing to admit to, and that's pretty true. I saw a lot of the imagery taken from the system, and I'd say a little bit less than 3 feet was about the best the system would do. But it was pretty phenomenal. From 100 miles away, you could see something that size on the ground, and it was pretty amazing stuff. I remember looking at pictures of cars in parking lot, and you could see all the cars parked. You could see the windshields. You could see, what kind of car it was, and so on and so forth. People were not available, or you couldn't really see the people very well once in a great while. But one of the things that was amazing is we had a picture that we had taken over a golf course, and the golf ball acted as a point source. So you could actually see the golf ball because it was white, reflected light, and acted like a point source. At any rate, that was Gambit 1. And that was pretty much over in 1967, thereabouts. It was a little soft. There was a fuzzy boundary between that and the next system. And there's a picture of the Gambit 1 payload. And you can see, roughly the size of it and kind of some of the stuff that's going on there. This is a sample of a photograph taken by Gambit 1 of an early warning radar in the Soviet Union. And I don't remember the exact date when this picture was taken, but it's pretty typical of the kind of imagery that we could get. And given where we were before, with essentially no imagery, this is kind of amazing, just really what you can find. You could look at this, and given the fact that we knew the actual orientation of the satellite, and we knew its altitude and its attitude very precisely, it's very easy to calculate then what the heights of these structures are above the ground, what their dimensions are, and then for those that are trying to determine, say, for example, for the early warning radar, well, what kind of an antenna does it have? How big is it? And all that. You were able to do that from this imagery. In addition, we were able to, say, take a picture of a military base or an airfield, and you were able to count the number of aircraft. You could estimate whether they were bombers or fighters or what they were, how many there were, where they were located on the base, and all that. In terms of the rest, you could see military vehicles, what kind of military vehicles they were, where they were located, and so on. And then by looking at the structures on the base and so on, you could make a pretty educated guess as to how many troops were stationed there. One of the programs I worked on was LMSS, Lunar Mapping and Survey System, and this was run coincident with Lunar Orbiter. It was not known at this time, since it had never been done. Lunar Orbiter was still being developed, and they weren't sure if the resolution achievable was going to be adequate, and they weren't sure that it was going to work. So what they did is they said, why don't we put Gambit 1 in the service module, and we can fly an Apollo mission, and we can take photographs, high resolution photographs of the surface of the moon and bring it back to Earth and look at it. So that was what this was about. And it was a really interesting program, because all of a sudden now we had to send this camera system, had to stuff it into the service module. And this is a drawing that shows exactly how we managed to do that in one segment of the service module. And, the other thing that we had to deal with was the radiation environment, and I was personally involved with that. And that was, you had solar flares, you had cosmic rays, you had to pass through the Van Allen belts, and then you had to orbit the moon for a significant period of time. And the radiation environment around the moon is a lot different than it is around the Earth. So we had to go through all that to try to understand if this system would survive as it was originally designed, and we needed to design additional radiation shielding into it and so on. So we got through all that, and we were in the process of starting up the engineering models, and then they canceled the program because they got the Lunar Orbiter imagery back and it was adequate. So that's the kind of the end of Gambit 1. So here's some things that Gambit 1 did. It improved the ground resolution from 50 feet to 2 feet at best within 3 years. Best ground resolution, better than 3 feet. It was closer to 2 feet by the end of the program. It allowed enlargement of the original image up to 2,800 times. So if you had a piece of film, 9.5-inch aerial film, you could enlarge that up to over 2,000 times in order to see what was there. That was in it. This was a very fine grained, very high resolution aerial film. The resolution was well over 100 line pairs per millimeter on the film. And that allowed to order a battle analysis, which is what I was just discussing, and also could get technical details on military equipment, weapons development, and command and control structures, and analysis of, camouflage, concealment, and, the types of things that the Soviets were doing to try to hide things. So it was enough information there to whet the appetite for more. And so that leads us into the Gambit cubed. Gambit 2 was another version of Gambit that turned out not to be very good, practical, as we got into the design. So we reset things and came back with what's turned out to be Gambit 3. And it provided a much better resolution, better than 2 feet. And by the end of the program, a lot better than 2 feet. It also provided stereo imagery, and it was focused on small target areas, as the Gambit 1 was. And it integrated well with Corona, and then later on with Hexagon, so that the two systems played very, very well together. Gambit 3 had 54 missions from 1966 to 1984. And it was really a great system. One of the most notable improvements between the two was the addition of what's called a roll joint. Let me jump ahead real quick here, and you can see the satellite system here. And about where behind the primary mirror, and you have the interface with the Agena spacecraft, which was what brought everything up into orbit and controlled it. In the original Gambit system, there had been another segment in there that was designed to have its own attitude control system to control the motion of the camera. And that never worked at all. So not too far into the Gambit 1 program, they just basically quit using it pretty much anytime they could. Well, what happened was the next iteration, which was Gambit Cubed, we had this roll joint, and it was literally a joint between the photographic payload and the Agena spacecraft, so that you could roll the photographic payload relative to the Agena spacecraft with a very high degree of precision, and the Agena spacecraft attitude control system would maintain it in a constant attitude, so that it was very stable and it was very quiet, which meant that when you made a motion like that, you didn't have to wait for a long time for all the vibrations to settle down, and it was extremely successful. And that made a huge difference in both the achievable satellite orbital life and in the quality of the imagery that we could get back from it. So anyway, the recovery vehicles were built by General Electric, and Kodak made the camera payload, and Lockheed built the Agena. And the booster was a Titan 3B, and they were all launched from Vandenberg. And the tracking facility and control facility was located in Sunnyvale, California, at a place called the STC. And it was referred to in the vernacular as the Blue Cube. Anybody that's ever been in that region might possibly remember seeing this big blue building sitting off by itself with no windows in it or anything else, and that was the Blue Cube. But that's where all the satellite control took place. And one interesting thing, just kind of a note by the way, but sort of interesting, I guess, is when the program first started, Kodak was not allowed to acknowledge its involvement in the program. I mentioned the fact it was a black program. Well, one of the reasons for that was for sure, if someone found out that Kodak was involved in a project, then you know it had to involve photography. And that was something they didn't want people to know. So we would travel out to the West Coast as self-employed engineers, consulting engineers. We paid cash for everything, no credit cards. And then we had to get into the STC during an operation. And initially, till some common sense prevailed, they would bring a panel truck up to the hotel. We would jump in the back and get in a box. And they would deliver the box to the STC loading dock, wheel it off, roll it down the hall into a secure room, and then open it up so everybody could get out. That didn't happen very often. There was one incident where the truck had a slight accident, so they said, no, this is not smart. So they figured out how to do it without doing that. But at any rate, it was kind of crazy. The same recovery system with the aircraft recovery was used for Gambit Cubed. It could operate up to or down to about 65 or 70 nautical miles altitude, but its upper limit by the end of the program was about over 400 nautical miles. A typical elliptical orbit might be, say, 70 miles by 200 and some miles for the perigee and the apogee. Mission duration was about 31 days on the average. The focal length, and we'll get into this a little more, but the initial focal length was 160 inches, and we had a block change not too long after the beginning of the program, and that increased to 175 inches. The aperture was about 44 inches. We could carry up to about 12,000 feet of film. And we had both 9.5 and 5-inch film, and we were able to engage about 15,000 targets per mission by the end of the program. Certainly could see objects less than 2 feet across. I'm not allowed to say how much less than 2 feet. I'll just simply say it was less than 2 feet. Very, very good imagery. We had 2 recovery capsules later on in the program. So that would allow you to, say, acquire targets early in the mission that were time sensitive, and then deorbit the RV with the film in it, and then that would give you a quicker look at it. And then the second RV could be launched at the end of the mission. The camera plus film together weighed about 4,000 pounds. So it was a nice system. And this is kind of here what some of the specs here on the first system. Used the R361 lens, 160-inch focal length. Was able to carry as much as about not quite 10,000 feet of film. The frame size was 4.4 by 4.7 nautical miles on the ground. And that, temper that a little bit, the dimension along the track, ground track of the camera system could actually be increased if you could increase the amount of film in the looper. You know, you take a couple of thousand stereo pairs, and it was a polar orbit, as we talked about earlier. And for this system, the average perigee was about 75, 80 miles, nautical miles. And the apogee was 240 nautical miles. And nominally, the first version of the system had a resolution of about 50, or a lifetime of about 2 weeks on orbit. Here's the later, what I call advanced Gambit. And it was able to do a bit more. It had the 2 RVs instead of a single RV. It had a new lens in there, a new lens design. It was 175-inch focal length. So somebody back after the First World War said, in aerial reconnaissance, focal length is king, and that's absolutely true, because the ability of your film to resolve so many line pairs per millimeter is a fixed property. You can't change that. Even though you have very high resolution, very fine grain aerial films, can provide some phenomenal imagery, record it. At the other end of the scale is on the ground, depending on your altitude, the amount of detail you can see depends on the focal length of the lens. So the whole thing about increasing the focal length meant that we could push the ground resolution up to a higher level. The R5 lens, which this was a beautiful design. Manufacturability was better than the original design that we had, and it generally was a very good system. So if there are any details about the camera design you want, you can feel free to ask, and I'll do my best to try to answer them. The basic operating modes of the system were the same as they were for the first Gambit version. And here's what the stuff, the layout of the major pieces of equipment inside the system were. This was the lenses used for the advanced Gambit were Ross lenses, which meant the full aperture corrector used on the first Gambit was gone. There was correctors located downstream prior to the camera, refractive correctors that clean the image up, and then they would then provide the aerial image to the camera. The stereo mirror, same concept as for the first Gambit. You look forward, you look aft, combine those two frames to get stereo photography. You also had the crab correction that we had for the first system. Had a focus adjust capability, and this also used a strip camera. Over time, the strip camera design evolved so that the smoothness of the film motion was compatible with achieving resolutions on the film of over 100 line pairs per millimeter. And we had quite a bit of film available, obviously. And so that was a big plus. One thing that we did here that was different than the earlier system was we had incorporated a camera, a 5-inch, used 5-inch film, a camera that looked through the main optics and looked down at the ground. And we were able, doing that, to use color film, infrared film, virtually any type of film that you might want to complement the black and white film that was on the 9.5-inch the black and white imagery. So again, the selection of imagery that the photo analysts had to work with was greatly improved, and there were more types of imagery available to help them in their job of analyzing the photography. And here's a picture of the payload in the clean room, and opening at the top is the viewport. That's where the stereo mirror looks out at the ground. And the lens barrel there is Invar. And if you're familiar with Invar, it's a very low coefficient of thermal expansion stainless steel, essentially. It's very strong, very light, and thermally very, very stable. Here's some examples of the kind of imagery. These images, if you can see them very well, they're taken across different spots in the Soviet Union. The one in the upper left-hand corner, this is a blow-up of it. And this was called the Caspian Sea Monster. And this was development work that the Soviet Union was doing on a ground effect machine that would fly over the surface of the sea. And I think what they were trying to do was to find ways to very rapidly transport things across water. Boats are not very fast compared to airplanes, and this would travel at a speed close to what an airplane might fly. But they built several of these and used to do test flights over the Black Sea, and then finally they abandoned the program. My guess is it was just not very workable in a practical sense. So the Gambit evolution, this just kind of summarizes a bit of what we had, ending with the advanced Gambit cubed, which that program ended in the 1980s. And the last one of those, or nearly the last one of those that we produced, system was designed to operate at 2 altitudes that were selectable. And one was up over 400 nautical miles, and the other one was down around 80 miles or so. And the idea was that if there was ever a failure of the hexagon system, or that we could go to a high altitude, and even though the field of view of Gambit was much less than Hexagon, both flying at the same altitude, by going further away, we could get reduced resolution imagery over a bigger area that would kind of fill the gap if Hexagon was not available. That was a good idea. It was it sort of worked, but it was an interesting concept, and fortunately, we didn't have to pursue it any further. So that's kind of the Gambit story there. There's a couple of other things I wanted to mention here in passing, and one of them is quite important. But this is just tells you kind of here's what Gambit did. And we've talked about most of this, and this is something that I think everybody was kind of surprised to get from Ronald Reagan, was a letter to the program, and it basically said, you guys did a really good job, and really contributed to national security. So that was nice to get. And here's a picture of some stuff that came up later. This is the commercial remote sensing stuff that went on back after the year 2000, basically. And the message here is these commercial systems they were electronic imaging, they provided color imagery, and ground resolve distance on most of these, which were much smaller systems, was better than Gambit 1. But that shows you how the technology progressed over time. And this is another sample of imagery, and the thing in the middle there is Osama bin Laden's compound. This is some imagery taken over Afghanistan. And I want to talk about Bridgehead. And Bridgehead is another classified program that Kodak had. Didn't build satellite cameras. What it did is it processed the film. And this was an amazing group of people for a long period of time. What they did was, and they supported all the U-2 efforts. The SR-71 predecessor was a very high altitude, extremely fast reconnaissance system, similar to the SR-71, and it was called Oxcart. And Kodak supported that. We built lenses and cameras and processed the film for the Oxcart program. And just typically in our Hawkeye plant, we had several floors of that building devoted to film processing. And the film processors were developed in such a way that we could provide frame by frame processing if necessary. We could do different development levels. And this is all driven by the target characteristics that were known to be in existence on each exposed piece of film. And then it would scan after initial development, and then it would adjust the processing parameters depending on what it find there. And the roadmap that referred to at the bottom there is typically we would get data back with the film that gave frame by frame exposure data that the film had seen. So that would help greatly with the processing. We could also adjust the development process to change what it called the gamma. Was something called a Herter and Driffield curve, which it just relays the density on the film to the exposure it got. And it's sort of an S-shaped curve. But you could adjust the shape of that curve and the levels there of density versus exposure by your processing. So if you had information on the kind of scene you were looking at, you could optimize the processing to improve the quality of the imagery for the analyst. And so this was the sort of thing they were doing. And these people also did all the U2 processing, as well as SR-71 and Gambit. And they did a lot of the hexagon processing too. Along the way, in 1965, about the time that Advanced Gambit was getting his feet on the ground, another classified photographic reconnaissance system was begun. Some of you may know about this. You may have heard of the Manned Orbiting Laboratory, which was the unclassified name for this. And the release to the public just stated this was a program and it was going to go up and they were going to have a orbiting laboratory and they were going to do all kinds of experiments and measurements and so on. Actually, it's designed to be a manned reconnaissance system. And at that time, the Air Force planned a much larger presence in space than it turned out to have. And the National Reconnaissance Office managed the development of the acquisition, and the anticipated performance was much higher than Gambit. The point being is that the focal length of the lens was 2 times or better longer than Gambit, so the resolution on the ground would have been better than 1 foot. And because it was manned, and you'll see in a minute when we talk about the characteristics of the system, had much more flexibility to select targets of opportunity. Here's a picture of the system with some dimensions on there. At the left is a modified Gemini capsule, which is how the crew of 2 astronauts would get up to the system. And then there's a tunnel between the Gemini capsule and the crew compartment, which is kind of in the middle there, to allow the astronauts to travel back and forth. In the crew compartment there were some really kind of interesting things. First of all, the type of camera that this system used was called a frame camera, which means the film is clamped on a platen held stationary during exposure. To compensate for the motion of the imagery, the mirror in front is not just a tracking mirror, it's actually, or a stereo mirror, it's a tracking mirror. It moves so that it moves in synchronism with the image motion, and it maintains a stationary image on the film. And that tracking would be adjustable by the crew, and there had visual optics there. They could look through the lens and at the ground and tweak things so that, you would set the parameters up, then you would look at it visually, you might tweak some settings, and then you would expose the film. And the camera lens itself, the primary mirror was 6 feet in diameter, and the length from the primary mirror to the tracking mirror was roughly, I don't know, 25, 30 feet, something like that. I don't remember the exact dimensions. And it was, again, a Ross lens, so it would have the refractive correctors in there and so on. There was also some visual optics in the crew compartment. So, for example, if you were coming up on one of your mission targets and it was cloud covered, you could scan around and look to see if you could find a target that wasn't cloud covered, or you could take a target of opportunity if something came up that was unexpected. And you could even process some of the film and send it back to Earth before the main RVs, the film recovery took place. So that was the concept for Manned Orbiting Laboratory. Its classified name was Dorian. We actually pretty much had built the mirrors, the optics. We hadn't done a full assembly of the telescope yet. We were in the process of building an engineering model of everything. and the program ended up being canceled because of the Vietnam War. The government felt that Gambit, advanced Gambit, had come along so well and was delivering such high quality imagery that, together with the need to have money available to for the Vietnam War, that they just didn't want to fund the program anymore. So unfortunately, it met its demise. I guess it was unfortunate. I don't know. Those of us that worked on it were sad when it left, but there. And here's a kind of a layout, how the layout was. And you can see this is all the stuff, white stuff there in white is Kodak's part of the system. And I won't say too much more than that about it. But there would have been a 2-person crew. The mission duration for the crew was about 30 days. So they would have to live in the Gemini capsule and work in the crew compartment here for a month. One of the astronauts that was involved in the program was Jim Abramson, and who I encountered later in my career. He was at that time a lieutenant general and was running the Star Wars program for Reagan. He was a really nice person, and he was very, very competent. Really a sharp person. So anyway, so that's kind of that. And that is about the end of the presentation. This is the performance improvement plan that was laid out for Dorian. And you can just see that, excuse me, the payload capacity would increase and the size of the system would increase over time. It never made it, but that was the plan. Okay, so that's pretty much all I have. And I'm wondering if anyone has any questions they'd like me to answer or anything else.
I have a question to start. It seems like these orbits were fairly eccentric. How did
Yes.
the cooling speed change to accommodate the different angular rate on the ground?
Okay, well, you're referring to the issues with image velocity changes?
Yeah.
Yeah, that was handled because the camera had commandable image or film speeds. So what you would do is you would go through a detailed planning process prior to the mission. You had a known set of targets that you were working on, and you would take your planned orbital parameters and the targets and would figure out what image velocities would be required for which target. And then you would program in the those velocities needed, and the camera would change from one velocity to another, target by target if needed.
So to feed on that, was it that last question in your response? Was autofocus done the same way? So meaning, I assume there was no active, was it pinging of your target? You don't want to reveal, but you're up there, and there's no active image processing. So it's based on how you're flying that you know that, oh, this target is 80 nautical miles, we'll set the focus to this.
Yeah, pretty much. Over the course of the program, we did a lot of work trying to come up with a good focus sensor that we could place on board the satellite that would give us good information and allow us to know whether we needed to set focus or not. Nothing worked very good. As good as just knowing the orbital parameters and the geometry of everything and being able to predict what the focal condition was going to be ahead of time. Yeah.
Did the Russians have anything like this at all?
Well, I'll just tell you what the gossip is. The gossip was, yes, they had some orbital imaging systems. At the time I was working on this stuff, it was very clear they were nowhere near as good as the systems that we had.
Yeah, your system was amazing.
Yeah, it really was. By the end of the program, the photo analysts would just shake their heads and just say, "This is wonderful. We love it," you know. Yeah.
Did the holographic plates like the KF 649 sort of thing, were those really developed from this program, the 100 line per millimeter kind of?
Well, no, talk a little bit about the film stuff, the photographic film. We had a very tight relationship with Kodak Research Laboratories, and Kodak Corporation was spending its own money to develop films. So we started off with standard aerial film, the type 3404, which was a high resolution film, but it was on an acetate film base. And acetate film didn't work very well in a vacuum environment. Plus, it was relatively thick, and so it limited the amount of film you could place on board the camera, given this weight and size restraints you had to deal with. So they undertook to develop a new film base, a polyester film base. And it started out at about 2 point something mils thick and ended up at 1.2 mils. So 1.2 mils, or thousandths of an inch, was the thickness of the film base. And that allowed us to increase the amount of film on the camera system as it was launched up to, actually about 12,000 feet of film. We started out with about 3,000 feet. So that was their contribution to that. And along the way, they developed new emulsions. 3404 was the original film that we used because it was a standard aerial film. It was pretty good imagery. But we got into 3414, which had a much finer grained emulsion, still had a decent sensitivity, so the exposure times weren't affected in a bad way. And then we went to 1414, which was the ultra thin base, and this new emulsion was a very high resolution, fine grained emulsion. And it was what you call a monodisperse emulsion. So that means all the silver halide grains were the same size, and they were randomly distributed in the emulsion. And so the silver halide grains were down in the micron size. And I don't know how familiar you are with the photographic process, but the way it works is when the photons from the image strike the film, if they're captured by a silver halide grain, it actually causes the silver halide to convert to silver. And then they make their merry way through the emulsion. Now you have to provide coatings on the back of the emulsion to capture any stray photons so they don't reflect back up through the emulsion again. And there's some other tricks that go on to improve the image quality. So you have an image in these very fine grained aerial films, high resolution aerial films, that can easily go up to 150 or more line pairs per millimeter. So that's the resolving power of that film. And as far as Kodak was concerned, I think a lot of the technology that went into that was also being used to develop other types of film. So things, as you were referring to, like, well, there was a lot of film developed for microscopy that was very fine grained, and so on and so forth. So Kodak typically spent a lot of effort improving the performance and quality of the film over the course of the program.
How much does atmospheric turbulence affect the image of this? Is it a factor at all?
I'm sorry, couldn't understand you.
Atmospheric turbulence, is it a factor at all in your imaging?
Okay. Yeah, this was a big issue during all these programs, and it was kind of an unknown when we started. And there's several other activities that were going on that also helped understand that. There was a lot of work from Cloudcroft looking up that would help us to understand a bit more about the turbulence, as the astronomy community also did a lot of work on it. And then when we got into the development of high energy lasers and active optics, that really kind of coalesced. And the bottom line is that the probable limit of resolution looking from orbit to Earth is very, very small and measured in maybe a few inches. And so it wasn't a big debt, and this all due to the atmospheric turbulence.
Thanks.
How did you manage the fog that you were getting from the cosmic rays on the film?
Well, that was mostly a matter of understanding what the environment was, as it turned out. What we would do is we relied on other experimental data. NASA did a lot of this early on, trying to understand what the radiation levels were, what kind of radiation there was, and so on. So the energetic radiation, what I would call like gamma rays, for example, there was not a high level of those in that environment. Okay, the primary contributors to radiation exposure were charged particles. And those would come from solar flares, cosmic rays, and then I had mentioned earlier the starfish explosion, the South Atlantic anomaly at that time was another factor. We dealt with it by making the best estimates of the radiation that we could, and then we would analyze the design of the system to see if we needed to add any additional radiation shielding to the system in order to protect the film. And as it turned out, we did not. And, you know, now if you're in orbit for a very long period of time at an altitude where you get a lot of radiation exposure, then you might have to worry about it. But for the mission durations we were talking about, it was really not a big issue.
Can you expand a little bit
Oh,
more?
I think there's a question back here. Could you just wait?
Oh, I'm curious how you did an on-off or a time sync photography position, syncing it with your film. I mean, were you turning on live and then off again every time you passed over a target, and then you just knew what was down there?
Pretty much, yeah. I mean, the whole trick to working a system like this is your mission planning. So you start with your basically your knowledge, and every time you run a mission, you collect more data. So, for example, if I had a particular target that I wanted to observe over time, like maybe it was a site where they were developing and testing ICBMs or something like that. Each time you flew, remember this way this works is you get over the target at the same time of day, depending on your orbital parameters, but generally that's how it worked. And so the lighting conditions would be about the same, and you'd know what your altitude was. And so essentially when you're approaching the target and you're ready to collect imagery, you turn the camera on and get everything ready to go, and then you fire off the camera and it comes up to speed and stabilizes speed on the film very quickly. And it maintains that speed for as long as you have film in the looper, and then you have to shut it off and reload the looper. But so that was kind of the process. As far as the exposure goes, again, that was primarily based on essentially knowledge of the lighting conditions, the sun angle, and the time of day, excuse me, would be the main determinants of that. And there's enough exposure latitude in the film that even though you might not hit the exposure exactly, it had enough latitude that, you know, if you were off by a certain, not a huge amount, but a reasonable amount, it would not adversely affect the imagery. So both your image smear or image velocity mismatch and your exposure then were managed by essentially operating the camera every time you came to a target and then turning it off until you got to the next target.
I think we have time for one more question.
Just wondering, could you expand a little bit about the optical design? So meaning, were you all spherical optics or asphere? What temperature range did you have to go through with this airborne?
Okay. Well, these telescopes typically have the Ross correctors, or the Ross telescopes, have an aspherical primary mirror, and then you have a group of refractive correctors that correct for other aberrations that you might be concerned about, say off-axis aberrations and things like that. And anything you had to correct based on the figure of the primary mirror. So in principle, in a perfect world, if the lens was designed, was built exactly to the design specs, it would perform to the design specifications, okay? Now we had something we called optical quality factor, and that was developed to help us calculate and predict system performance. And it was generated by looking at what we would do is specify the surface figure tolerances on the optical elements and the wavefront tolerance, wavefront air tolerance on the telescope. And then you could predict with the right analytical tools, you could predict, given those numbers, you could predict the performance of the telescope as manufactured. One of the things that you knew was what your manufacturing capabilities were, and statistically, they were very good. There's not a lot of variability in the basic process that we use to manufacture those optics. So you didn't have to worry, like with consumer cameras, for example. We did some work on that at one point in time, and there you have a high volume manufacturing process, so that you may be spitting out 10,000 lenses per hour or something like that. And the processes used were variable. So you could never predict any one time that lens is better than this other lens, but that's not the case for the stuff that we did. We had, when we started in Gambit 1, we had no interferometers basically. And then the first thing we got was laser interferometers, and that was very early on in the program. And then we developed a whole set of different manufacturing tools. And so if you want to get into the optical processing, we could talk about that a bit at some point. But we had started out pretty much with the standard way of doing things in the 60s, which was abrasive machining, and you'd put the optic on a turntable and you'd have a tool and abrasive, and you'd polish it or grind it until you thought it was about right. You'd take it off and measure the surface, and then you'd adjust your tool and your abrasive and gradually grind it into the right figure. And it worked, but it was very time consuming. And so anyway, I guess the whole thing about the optics is that the way we manufactured those optics, they were mostly very near the formula quality, okay, if not at the quality of the lens formula. So, but that's because we were building them one at a time, and we could take the time to make sure that everything was the way it should be. I mean, obviously, there were times when we didn't quite achieve that, but for the most part, that's how it went.
Michael, we're out of time here. I really appreciate your time sharing this with us today. This was absolutely fascinating. So everyone, one more round of applause.
Okay, thanks, guys. I appreciate the chance to talk to you.
All right. Thank you so much.
You bet.
Bye-bye.
You.